The next type system that we look at is the Hindley Milner type system. It's a type system that supports polymorphic types, okay, and is the basis for the type system of languages like standard ML. Before we look at the Hindley Milner type system, we look at the standard ML's type and be explicit about the polymorphism. So let's take the map function. We would have written something like this in standard ML. We would have written that the map has type quote A arrow quote B, A list to B list, right? And it is assumed that A and B can be replaced by any type that we want. Okay. In the context of giving typing rules, it is better to be explicit about this fact. Okay. How do we make this explicit? In our context, we will say map has type for all, let's say alpha, for all beta, alpha arrow beta. So let's put a dot here. Arrow alpha list to the beta list. Okay. So we have made the dependency on alpha and beta explicit by doing this quantification. So whenever we look at a standard ML polymorphic function, it is assumed that there is outer layer of for all quantification. We now start defining the Hindley Milner type system. For this, we fix a base type, set of basic types. So a set like B equal to, let's say, nat and bool, okay. And type variables. A set B equal to, let's say, alpha 1, etc., and etc., or sometimes we use beta. Types are divided into two classes: monomorphic types or monotypes, and type schemes. Which is where you get polymorphism. So now let's look at monomorphic types. Monomorphic types are defined as follows. We denote tau to represent monomorphic types. Just like in the simply typed calculus, a basic type is a monomorphic type. Tau 1 arrow tau 2, where tau 1 and tau 2 are monomorphic types, that is also a type, monomorphic type. In addition, what we have here is a type variable. Okay, so that's the additional thing that we have from the simply type lambda calculus case. The type scheme gives us polymorphism in this language. In essence, a type scheme sigma is a for all quantified monotype. Sigma looks like for all alpha 1, etc., for all, and tau for some monotype. Formally, a type scheme can be defined as follows. Sigma is either a monotype or it is for all alpha sigma 1, where sigma 1 itself is a type scheme. We now describe the typing rules for a lambda calculus with the Hindley Milner type system. Okay. Firstly, we call the rules that we had for simply typed lambda calculus. Okay. We had rules for built-in, we had rules for variables. So if you look at the variable rule, it says something like this. Okay. And we had rules for application. Okay. we had rules for abstraction and then some structural rule, weakening and contraction. Okay, these rules carry over, but now they are for monotypes. Okay, all these rules carry over to the Hindley Milner setting, where the types tau are monotypes. How do we prove judgments of the kind E has type sigma for some type scheme? There are two rules. One is the rule of generalization and the other is the rule for specialization. So we will call it gen. And the generalization rule is the following. Suppose we manage to prove that under the assumption gamma that E has type sigma, then from this we can move to a more general type for E, which is for all alpha sigma. Okay, but there is a condition, which is that alpha should not be free in gamma. What do we mean by that? Say if you take the assumption gamma as the set x1 has type sigma 1, comma dot 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 xn has type sigma n, then alpha should not be free in any of the type scheme sigma I. Let us look at the intuition behind the generalization proof by revisiting a proof that we did in the simply lambda type calculus case. The proof that we did was to prove that the function lambda x lambda y dot x has type nat or a bool arrow nat. The same proof with nat being replaced by alpha and beta looks like this, and we have this as a valid proof in the Hindley Milner type system. Okay. Now notice that at the point 4 we have, without any assumptions, we have managed to prove lambda x lambda y dot x has type alpha arrow beta arrow alpha, no matter what alpha and beta is, and this is what allows us to finally conclude that let's look at this function. Since there are no assumptions and hence all the variables alpha and beta are alpha and beta can be quantified, we have and this is using the generalization. Okay. Since this proof works uniformly for alpha and beta, we are allowed to do that. Imagine that we had stopped at this point. Okay. Now alpha is in the assumption, so you cannot quantify this over alpha, but you can quantify over beta because beta is nowhere in the assumption. Okay. So let me look at an intermediate stage here, and let me call this 3.5, and here I can quantify over for all beta or beta or alpha, but not over alpha because alpha is in one of these assumptions. While the generalization rule allowed us to generalize the type of E, the specialization rule allows us to do the opposite. The specialization rule is as follows. Let's say under the assumption gamma we derive E has type sigma, then under the same assumption we can derive E has type sigma prime, provided we have this condition that sigma prime is a specialization of sigma, which we denote by sigma prime is less than or equal to sigma in the generalization. Okay. To finish the description of the specialization rule, we need to be precise about when is a type scheme sigma prime a specialization of sigma. Okay. So there are two cases The first obvious case is when sigma prime is a monotype, and then the general case when sigma prime is a type scheme. Okay. Let's motivate these two rules by looking at the specific case of map function. We know what the map function's type is. This is a polymorphic type, a polymorphic map function. Okay. Firstly, notice that map, if you want, can be thought of as a function from nat arrow bool to nat list to bool list, which means that if sigma looks like, let's say our sigma looks like, say, for all, say, alpha 1 for all alpha n, say some tau, then we know that if you take tau, so what does this say? In tau I can replace alpha 1 through alpha n with any type I want. So this, if I in tau, if I take if I replace alpha 1 with, let's say, tau 1, etc., say alpha n with tau n, this is definitely a special case of sigma. To motivate the general case, consider the following incarnation of the map function. Okay. Here what I have done is I have replaced alpha with some gamma 1 and beta with gamma 2 arrow gamma 3, and I have done this uniformly, so I can even think of map as a function of type for all gamma 1, for all gamma 2, for all gamma 3, whatever. Okay. So it is not enough to just restrict to monotypes, so we have to work the general case. So the general case is as follows. We can take the same expression in tau, which is a base monotype of sigma. You can replace alpha 1 with tau 1 and alpha n with tau 1 together with quantify over certain variables in tau 1 to tau 1. Say this might be new variables, beta 1, etc., and there might be more than n variables, n or m is less than sigma, provided, and this is very important. See, this sigma all has quantified over alpha 1 through alpha n, but it might have other variables in tau. Okay. So what we want is these beta should not be those variables. So beta i's are not free in sigma. Okay. So if that is the case, not only can you substitute alpha 1 through alpha n with any monotype, you can also quantify over the variables that occur there which are not free in sigma. And thus we can think of this as follows. So you do it two stages. Take map and think of it as the type this first. Yeah. So here I have uniformly substituted alpha with tau 1 being gamma 1 and tau 2 beta I have replaced by tau 2, which is gamma 2 minus gamma 3, and then I can quantify over all these gammas.